Welcome back, everyone, to Day 5 of our Explainer series. It is great to have you here. Since you already know how neural networks and deep learning actually tick, it's time to tackle the big one, the ultimate question, the one that decides whether a machine learning model is actually useful or just a massive waste of computing power. Today we answer, how do we know if an AI actually works? Section 1. The AI reality check. Okay, let's dive into this, because here's the stark reality of building artificial intelligence. What if I told you that a model can look absolutely brilliant during its training phase? I mean, acing every metric and looking like a total genius, and still completely fail the moment it hits the real world. Seriously, you could spend months building what looks like a perfect neural network, only for it to fall flat on its face when real users try to interact with it. And that is exactly why AI does not just learn once. I mean, you wouldn't let someone read a driving manual and then immediately hand them the keys to a car, right? An AI model cannot just read a textbook. It has to be rigorously tested, meticulously checked, and repeatedly challenged before anyone can actually trust it to make real decisions. Section 2. Dividing the data. So, how do we actually pull off this testing and checking? Well, to avoid a total failure, you cannot use all of your data in the exact same way. You have to split it into 3 distinct parts right from the very beginning. The biggest chunk by far is the training set. Then you've got a smaller validation set, and finally, a test set. Each one has a completely different, highly specialized job. Why does splitting it up matter so much? Because if you test a model on the exact same data it already studied, you have a massive blind spot. You simply do not know if it actually learned the underlying concepts or if it just blindly memorized the answers to the test. Section 3. The AI development pipeline. Now, this split data maps perfectly onto the complete journey of a machine learning model, moving it from a mere lab experiment into a fully functioning product. Step 1 is training. This is where the model is actively learning from that biggest chunk of data. Step 2 is validation. During validation, you check how well the AI is learning and you actively tune its hyperparameters, adjusting the dials. Then comes step 3, testing. And notice the crucial distinction here. You are no longer tuning. Testing means you measure the final performance on brand new, unseen data. It's a strict evaluation. Finally, step 4 is deployment. This is when you release it out there into the real world. This 4-stepped pipeline is exactly how AI safely moves from a concept to reality. Section 4, Overfitting versus Underfitting. But, of course, the journey is rarely perfectly smooth. There are massive pitfalls along the way that can completely derail that development pipeline we just looked at. The first is overfitting, which is a classic high-variance problem. This happens when the model learns the training data way too well. It frantically memorizes every single pattern, every outlier, even the noise. It's like that famous story of an AI trained to detect hidden tanks. It turned out the AI just learned to recognize cloudy skies versus sunny days because of the lighting in the training photos. It failed completely on new data. Now, the absolute opposite is underfitting, a high bias problem. Here, the model's just lazy. It's too simple or too weak to learn the important patterns at all, so it performs terribly right from the start. One memorizes entirely too much, and the other learns far, far too little. Section 5. The goal of generalization. So, navigating between those two extremes, avoiding the manic memorization of overfitting and the lazy simplicity of underfitting, brings us to the true ultimate goal of all machine learning, generalization. Generalization is simply the ability of an AI model to perform well on new, unseen examples. Think about it. The goal isn't just to look smart during training on one single dataset. The whole point, the only reason we build these systems, is for them to actually work in the real, unpredictable world. To ground this entirely, a perfect mental model for this complex pipeline is just a student in school. Training is simply reading your notes. Validation, that's practicing sample questions, testing yourself and adjusting your study habits based on what you got wrong. Testing is sitting down and taking the final exam. No more studying, no more tweaking, just a pure measurement of what you actually know. And deployment is graduating, going out into the workforce, and using what you learned in real life. It's a simple idea, but it wonderfully captures the technical flow. Section 6. Putting it into practice. Okay, let's put you in the hot seat. Let's take what you've learned today and apply it to a real-world scenario. Imagine you are the lead engineer training an AI model, and its job is to predict whether a student will pass an upcoming exam. Based on our pipeline, how exactly do we split the data? I want you to mentally map this out right now. What specific data goes into the training set? What would you use for validation? What do you rigorously save for testing? And crucially, what would the disaster of overfitting look like in this exact example? All right, let's break it down. For your training data, you'd feed the model historical records, past study hours, homework scores, and attendance. Your validation data would be a separate subset used specifically to tune the model, like maybe adjusting how heavily it weighs attendance versus homework grades. Your testing data is a completely untouched group of students used exclusively to check the final accuracy of your predictions. And deployment means actually turning it on and using it to flag current students who might need extra help. By the way, overfitting here would mean your AI perfectly memorized last year's specific students and their quirks, but completely fails at predicting the performance of this year's distinct class. If you map that out clearly, congratulations, you genuinely understand one of the most fundamentally important parts of artificial intelligence. You all have done an incredible job navigating the data pipeline today, but our exploration into the mechanics of AI is far from over. Coming up next time in our Explainer series, we're going to explore exactly how AI uses probabilities to make these complex decisions. We'll be lifting the hood again to look at the mathematical logic driving the machine, so definitely keep your curiosity high. Remember, a model is only useful if it performs well outside the training data. Generalization is the key to it all. It doesn't matter how smart an AI looks in the lab, if it can't handle the real world, it's not ready. But I want to leave you with this final thought. If an AI can perfectly memorize the past, but completely fails to adapt to the future, did it ever actually possess intelligence at all? Think about that one. Thank you so much for exploring this with me today. Keep asking great questions, and I will see you in the next explainer.